look around you right now. Like, actually take a second. Take a look at the smartphone sitting on your desk, or maybe it's in your hand.
Right.
Glance over at the thermostat on your wall that's keeping the room comfortable. Think about that incredibly specific, targeted ad you just swiped past on a social feed.
Oh, yeah. Those are getting scary good.
They really are. Or even the artificial intelligence you might have chatted with this morning to summarize some ridiculously long email thread.
Yeah.
It feels like we are living in a fractured landscape,
Yeah.
Just 1,000 different technologies all doing their own highly specialized things.
Totally.
But what if all of these seemingly disparate pieces of the modern world, the phone, the temperature control, the social network, the AI, what if they are actually running on the exact same hidden mathematical DNA?
It's crazy, but it fundamentally changes how you view the modern world when you realize that.
Yeah.
Yeah, because we tend to compartmentalize all these technologies into distinct disciplines, right? Like, we say this is electrical engineering, and that is computer science, and this over here is behavioral economics.
Right, they all have different textbooks.
Exactly. But if you dig down to the bedrock, they are all leaves on the exact same intellectual tree.
Well, welcome to this deep dive. Today, we are taking a massive intellectual journey.
We really are.
We are going to trace a grand genealogy of what you could basically call systems mathematics.
I like that term.
Yeah, so we're going to explore how mathematics evolved, specifically over the last century and a half, from something used merely to measure the physical chaos of bouncing atoms in a steam engine.
Which is wild to think about.
It is. From steam engines into the very language we use to model communication, control, reasoning, vast global networks, and ultimately, artificial intelligence itself.
And, I should point out, this isn't some timeline of boring equations or a dry list of inventions.
No, definitely not.
This is the story of how human beings figured out how to take incredibly abstract, almost ethereal concepts, things like uncertainty, meaning, strategy, and even thought, and translate them into rigorous mechanical procedures.
Mechanization of the human experience.
Basically, yeah.
So we want to understand how we built digital brains. And to do that, we have to understand the underlying logic.
Right.
We aren't going to just walk through a syllabus here. We're going to look at the massive paradigm shifts. We'll start with the foundation in thermodynamics, like literally boiling water and steam, and watch how that birthed the information age.
Moving through the explosive scientific leaps of the mid-20th century right up to the neural networks that are actively writing code and poetry today.
So to really understand how we eventually built machines that can learn and predict the future, we actually have to start by looking backward.
Yeah, at how we learn to measure disorder. Because you really cannot build a coherent system without first understanding chaos.
And that brings us to the concept of entropy. Now, I think for most people listening, the word entropy immediately brings up like vague memories of high school physics.
Right, yeah, the coffee cup.
Exactly. You picture a hot cup of coffee cooling down on a counter. Or a bedroom that inevitably gets messier over time unless you actually put energy into cleaning it.
My kids' bedrooms, specifically.
Exactly. It's this one-way arrow of time towards disorder. But how on earth does a concept deeply rooted in 19th century steam engines become the bedrock of the 21st century information age?
Well, the translation of that concept is, it's one of the greatest pivots in the history of science.
Okay, set the scene for us.
Let's place ourselves in the late 19th century. The Industrial Revolution is just roaring. Physics is completely obsessed with thermodynamics, specifically heat engines.
Trying to make trains go faster?
Right. So you have scientists like Ludwig Boltzmann looking at gases inside a cylinder. And a gas is basically made up of billions upon billions of atoms bouncing around wildly.
And the sheer scale of that is the problem, right? Like, you can't possibly measure the exact position, the exact velocity, the trajectory of every single microscopic atom.
No, it's computationally impossible today, let alone in the 1870s.
Yeah.
So the human mind and our instruments simply cannot track that level of granular detail. So Boltzmann and his contemporaries started looking at the macroscopic properties.
The big picture stuff.
Exactly. Things we actually can measure, like overall temperature, volume, and pressure. These macroscopic properties emerge from the statistical averages of all those microscopic, invisible bounces.
You stop trying to track the individual drop of water, you just measure the wave.
That's a great way to put it. And to do this mathematically, Boltzmann formulated a rigorous definition of this disorder, which we call entropy.
Right.
He created a formula, which is actually famously engraved on his tombstone.
Wait, really? on his tombstone.
Yeah, it's S equals K log W.
Okay, let's break that down.
So the S represents entropy. The K is just Boltzmann's constant. But the beating heart of the equation is that W...
The W.
Yeah, W stands for the number of microstates. This means the total number of specific, detailed ways all those microscopic atoms could be arranged that would still result in the exact same macroscopic state we observe from the outside.
Okay, let me put a mental image to this for everyone listening.
Go for it.
Imagine I'm holding a brand new, perfectly ordered deck of playing cards. They are sorted by suit, from ace to king.
Right.
The macroscopic state is perfectly ordered deck. The microstate, the specific arrangement of cards to achieve that look, is just one.
Yes.
There is literally only one way the cards can be arranged to be in that perfect order. So the W is one. The entropy is incredibly low.
And what happens if you drop that deck onto the floor?
I get a massive scattered pile of cardboard on the rug. So the macroscopic state is a messy pile. But the W, the microstates, is astronomical now.
Exactly.
Because there are billions of different ways those 52 cards could land, overlap, and scatter that would still just look like a messy pile to me standing over them. So the disorder, the entropy, is incredibly high.
That captures the physics perfectly. Initially, entropy was strictly a physical property of things in the real world, you know? Gas in a container, heat dissipating from an engine, cards on a floor.
Stuff you can touch.
Yeah, but mathematics has a funny habit of breaking out of the physical constraints it was born in.
Which is where things get weird. It started getting applied to highly dynamic, chaotic systems that weren't just cooling down in a closed box.
Right.
The sources for this deep dive point to the work of Ilya Prigogine, a physicist and chemist who actually eventually won the Nobel Prize.
Yeah, Prigogine fundamentally changed how we view chaos.
How so?
Well, traditional thermodynamics usually looked at a closed system settling down into a boring, uniform state, equilibrium.
Like the coffee cup finally reaching room temperature.
Exactly. But Prigogine looked at systems that are far from equilibrium. Think of a rushing river, a boiling pot, or even a living biological cell.
Okay.
These systems are wildly dynamic, constantly exchanging energy with their environment.
They are messy reality.
Yes. And Prigogine proved mathematically that even in these chaotic, non-equilibrium systems, there is still what we call statistical regularity.
Meaning patterns.
Exactly. Hidden patterns emerge out of the chaos. The math can describe the probability distributions of these systems even when they're swirling and shifting.
Wow.
It proved that mathematics didn't just apply to dead, resting systems. It could model the living, breathing, moving world.
But the real mind-bending shift, the one that really sets the stage for the digital age, comes a bit later with a physicist named E.T. Jaynes.
Yes.
From my reading of the sources, Jaynes looks at Boltzmann's entropy and essentially flips the entire universe inside out.
He really does.
He argues that entropy isn't just a physical property of the world, it's something entirely different.
It is a profound philosophical reversal because, for almost a century, physicists constructed theories assuming that the equations of motion were the absolute reality.
All right.
And probability was just a dirty bandage they slapped on top because their tools weren't good enough to measure everything perfectly.
Like, oh, we just can't see all the atoms yet.
Exactly. Entropy was seen as a physical property of the gas itself. But Jaynes, in the mid-20th century, reversed that completely.
What did he say?
He said, let's take entropy as our primary starting point. Let's maximize the entropy subject to whatever constraints we know.
Maximize the entropy subject to constraints. What does that actually look like in practice?
It means Jaynes realized entropy is actually a tool for our own reasoning. It is a mathematical measure of our ignorance.
Our ignorance.
Yeah. He argued that when you are forced to make a prediction about a system, but you have incomplete information, which is, let's face it, almost always the case in the real world, the most honest, mathematically sound thing you can do is to choose the probability distribution that has the highest possible entropy.
Okay, I think I follow.
You must choose the model that maximizes uncertainty while still fitting the few sparse facts you actually know.
Because if I don't maximize the uncertainty, if I pick a more specific model, I'm essentially pretending to know things I don't actually know.
Yeah.
I'm injecting my own bias.
Precisely. You are artificially lowering the entropy by assuming unearned information.
That makes total sense.
So Jaynes took statistical mechanics out from under the strict umbrella of physics. He turned it into a universal method of statistical inference.
Wow.
As Jaynes pointed out, the fact that the exact same mathematical expression The sum of the probabilities multiplied by the logarithm of the probabilities shows up in both physics and modern information theory is not a coincidence at all.
It's the same math.
Yes, it shows up everywhere because entropy is fundamentally about the limits of what an observer can know.
Let me hold on to this because it's massive. We took a concept invented to figure out why steam engines lose heat, and we transformed it into a mathematical metric for human ignorance and uncertainty.
Right.
It's a way to calculate exactly how much we don't know.
And that pivot is what opens the door to everything that follows. Because if entropy is the precise mathematical measure of uncertainty, then what is information?
Oh, I see where this is going.
Information is simply the resolution of that uncertainty.
If my uncertainty about the world is high, and you tell me a fact that lowers my uncertainty, you have transmitted information.
Exactly.
Which naturally leads us to a completely different problem. How do we actually send that information over a physical distance?
Now we're getting to the good stuff.
This takes us to the year 1948. And arguably, 1948 is one of the most important years in the history of human thought.
It really is. I mean, the entire trajectory of human engineering fractured and went down a completely new path that year.
We are at Bell Labs, right?
Right, at Bell Labs. And we have Claude Shannon publishing a paper titled A Mathematical Theory of Communication.
The big one.
It is impossible to overstate the impact here. He essentially birthed classical information theory overnight.
And it's fascinating because Shannon wasn't a philosopher looking at the universe. He was an engineer. He was dealing with the very practical problem of a noisy telegraph wire or a static-filled radio transmission.
Yeah, he was in the trenches.
During World War II, he worked on cryptography, scrambling voices so the enemy couldn't understand them. He was obsessed with the signal.
Right.
And in this 1948 paper, he draws a schematic that our sources literally call the mother of all models. It claims to map every single form of communication in existence.
And honestly, it does. Shannon abstracted all communication down to 5 basic components.
Walk us through them.
First, you have the information source. This could be a human brain wanting to speak, a television camera capturing a scene, or a computer terminal.
Okay, that's one.
Second is the transmitter, or encoder. This takes the message and translates it into a physical signal. So a microphone turning a voice into electrical waves, or a telegraph operator turning letters into Morse code dots and dashes.
Right. Third is the channel, the actual physical medium. So that's the copper wire, the fiber optic cable, or just the empty airwaves.
Yeah.
And this is where the villain of the story enters, right?
Yeah.
Noise.
Yes. The channel is constantly bombarded by noise, static, thermal interference, a thunderstorm disrupting a radio wave, or even just a smudge on a piece of paper. Noise alters the signal.
Okay, so we've got source, transmitter, channel, and noise. What's next?
Fourth, you have the receiver, or decoder. Its job is to take that degraded, noisy signal and reconstruct the original message.
And finally?
Finally, the fifth component is the destination, the person or machine the message was ultimately intended for.
It's a brilliantly clean model. But the genius isn't just the diagram. The real genius is that Shannon took Boltzmann's physics concept of entropy and forcefully applied it to this engineering problem.
He introduced the Shannon entropy formula, H equals negative sum of P sub I log P sub I.
And if you look at it on a chalkboard, it is structurally identical to Boltzmann's formula for atoms.
It's the exact same shape. But Shannon's H wasn't measuring gas, it was measuring the uncertainty of the information source.
He's measuring how unpredictable the sender is.
Right.
Like, if I'm a telegraph machine, and I only ever send the letter A over and over again, my entropy is 0.
Because I know what's coming.
Exactly. You have 0 uncertainty about what the next letter will be. Therefore, when I send the next A, you gain 0 information.
Exactly. Information is tied directly to surprise, to unpredictability. Shannon mathematically proved that if you want to send a message reliably through a noisy channel, you have to overcome the entropy.
Ow.
He established the absolute fundamental limits of 2 things. First, data compression, how small you can squeeze a message down by removing redundancy. And second, channel capacity, how fast you can shove that compressed data through a wire without it being irreparably swallowed by noise.
He proved that if you encode the message correctly, adding just the right amount of mathematical redundancy, you can transmit information with near 0 errors.
No matter how noisy the channel is.
Right, as long as you stay below the channel speed limit. It essentially proved that reliable communication must be digital.
But to make this entire mathematical edifice work, to make it perfectly universal, Shannon had to do something incredibly controversial.
This is the part that always gets people.
Yeah, he had to sever a connection that human beings intuitively feel is absolutely unbreakable. He completely, ruthlessly separated information from meaning.
I really want to spend some time on this because it feels so counterintuitive. Prior to Shannon, if you stopped a random person on the street, or even a linguist, and asked, what is information?
They'd say it's the meaning of a message.
Right. It's the gossip, the news, the profound realization. Information is the semantic content. But Shannon says, mathematically, that is totally irrelevant.
Shannon stated explicitly that the semantic aspects of communication are irrelevant to the engineering problem.
Irrelevant.
Completely. Communication, in his view, is simply the act of reproducing at one point a message selected at another point. That's it.
Let's picture a noisy phone call. I'm calling you from a payphone in a bad storm. There's terrible static. I could be shouting a profound, heart-wrenching poem into the receiver, something that holds the ultimate meaning of life and brings you to tears.
Okay.
Or I could just be shouting a random string of numbers, 7, 4, 9, 2. According to Shannon's mathematics, if both of those audio streams require the exact same amount of binary code to transmit, they contain the exact same amount of information.
Yep.
The math does not care if the message changes your life or puts you to sleep. It only cares about the probability of the symbols occurring.
That is the perfect distillation of his theory. And when he published this, people, especially in the humanities, complained bitterly.
I bet.
They felt Shannon had sterilized communication. They argued he left out meaning.
Because to a human, the meaning is the whole point.
Oh, of course. But Shannon's abstraction, his decision to strip away human semantics and deal purely with syntax and probabilities, is exactly why the theory is so universally powerful.
Because it works for everything.
Exactly. If the math cared about meaning, it would have to be different for every single type of message. But because he separated the physical signal from the semantic meaning, the exact same mathematical equations can govern everything.
Right. Like a fiber optic cable at the bottom of the Atlantic Ocean doesn't know if it's transmitting a $1 billion bank transfer, a cat video on YouTube, a piece of malware, or an ultrasound image.
The cable doesn't care.
It's all just uncertainty being reduced at the destination.
Hmm.
By ignoring meaning, Shannon made information a physical, measurable, interchangeable quantity.
He essentially commodified uncertainty. It is the bedrock of the entire digital infrastructure we use today.
But, it leaves us with a lingering question. Shannon solved the problem of getting the message through the static. He made sure the cat video arrives flawlessly.
Right?
But that begs a bigger question. Once the message arrives, what does the receiver actually do with it? Because a message doesn't just sit there in a vacuum. Usually, a message triggers an action. I don't just call you to reduce your uncertainty about the acoustic waves my mouth makes. I call to tell you to change your behavior, to pick up milk on the way home, or to hit the brakes because there's traffic.
Right, you want an outcome.
And that realization that messages cause actions in a system happened in the exact same magical year, 1948.
It is stunning that these ideas emerged simultaneously. If Shannon showed us how to reliably send a signal, the mathematician Norbert Wiener showed us what happens when that signal creates a loop of action and reaction.
Wiener.
Yes. Wiener published a book in 1948 simply titled Cybernetics.
And the subtitle of that book is incredibly bold, right?
Yeah.
Control and Communication in the Animal and the Machine.
Yeah.
He is explicitly putting living, breathing biology on the exact same theoretical plane as cold, hard machinery.
Wiener made a defining, audacious claim. He realized that the problem of control engineering, how to steer a ship or aim an anti-aircraft gun, and the problem of biological regulation, how a human body maintains a constant internal temperature, were structurally identical.
Structurally identical.
Yes. He coined the term cybernetics from the ancient Greek word kybernetes, which means steersman or governor. It became the transdisciplinary study of circular causal processes.
Circular causality. That is such a vivid concept.
It is.
Up until this point, most science thought in straight lines. A causes B, B causes C. End of story. But Wiener says, no, look at the real world. A causes B, B causes C, and then C feeds back and alters A.
The effect loops around to change the cause.
Exactly.
And the central concept that makes this loop work, the beating heart of cybernetics, is feedback.
Right, feedback.
Feedback is the process where a system takes the observed outcomes of its past actions and uses them as new inputs for its future actions. It is how a system navigates an unpredictable environment to pursue a specific goal.
Let's ground this with the classic cybernetic device, the thermostat on the wall. For most people, a thermostat is just a switch. You turn it up, the heater comes on. But if you look at it through the lens of cybernetics, it is a purposeful observer.
Walk us through its perspective.
Okay, the thermostat has a goal, a parameter you set, say 72 degrees. That's what it wants the world to be.
Okay.
It has a sensor that constantly reads the actual room temperature that's the input. It compares the input, let's say 68 degrees, to the goal of 72 degrees. It notices a discrepancy.
And in cybernetics, this discrepancy is called the error signal.
The error signal. Because there is an error, the thermostat takes an action.
Yeah.
It turns on the furnace.
Right.
But here's the crucial part, the circular loop. It doesn't just turn on the furnace and go to sleep. It keeps observing. As the heat rises, the input changes, 69, 70, 71. The error signal shrinks.
Yes.
Once the input matches the goal, the error signal drops to 0, and the thermostat turns the furnace off. It regulates itself purely through this loop.
That is a flawless description of negative feedback.
Yeah.
Negative meaning it negates the error, it seeks stability or homeostasis.
Right.
And Wiener's genius was looking at that simple mechanical loop and seeing it everywhere. A 19th century steam engine uses a mechanical centrifugal governor, 2 metal balls spinning on a shaft to regulate its speed via feedback.
Okay, that's machines.
But look at a human being. When you reach your hand out to pick up a glass of water, you are executing a cybernetic feedback loop.
Wait, really? How?
Your eyes measure the distance between your hand and the glass. Your brain generates an error signal. Your muscles move your arm. Your eyes continuously update the shrinking distance, constantly microcorrecting your trajectory until your fingers close around the glass.
Oh, wow. So if your feedback loop is broken, if your brain can't process the error signal from your eyes quickly enough, your hand shakes or you knock the glass over?
Exactly. Or look at economics. A free market uses price as a feedback signal. If supply is low and demand is high, the price goes up an error signal that tells producers to make more of the product. The increased production eventually meets the demand and the price stabilizes.
So cybernetics provided this massive unifying language. Suddenly you have mechanical engineers, neurophysiologists, economists, and psychologists all looking at their distinct fields and realizing they are all just studying systems that regulate themselves via error signals.
And they actually came together to discuss this. Between 1946 and 1953, there was a series of legendary meetings known as the Macy Conferences.
I've heard of these.
Yeah, you had mathematicians like von Neumann and Wiener sitting in the exact same room with anthropologists like Margaret Mead and Gregory Bateson.
That is quite a room.
They were trying to forge a universal science of the human mind and society based entirely on feedback loops, communication channels, and control mechanisms.
But wait, hold on. I need to interrupt here with some genuine skepticism.
Oh, yeah, let's hear it.
It is incredibly elegant to see the math of a thermostat working inside a human reaching for a glass. But a human society isn't a thermostat.
No, it's not.
We have irrational actors, we have historical grudges, we have political power dynamics, we act out of spite. Aren't we risking a massive, dangerous, technocratic overreach by trying to model the complexities of human civilization, like the mechanics of a steam engine?
That is the exact trap and the fatal flaw that haunted the cybernetics movement. The shared mathematical language is deeply seductive.
It is.
It creates a very strong temptation to treat systems that are superficially similar in their feedback loops as if they are substantively identical in their nature.
Because if a society is just a machine, then an engineer can just quote-unquote fix it.
Exactly. Yes, a society has feedback loops. A citizen protest is a form of an error signal. An election is a regulatory mechanism. But a thermostat just relies on a simple piece of metal reacting to heat. A society is composed of conscious, emotional agents with conflicting, deeply held goals. When you reduce human nuance to a purely cybernetic control problem, you risk designing oppressive systems. You get technocrats who try to optimize society for a single, easily measurable parameter like GDP or efficiency, while completely destroying unquantifiable things like human flourishing, dignity, or cultural heritage.
So the mathematics is merely a model of reality. It is never the territory itself.
That is a crucial warning. We can mathematically model the feedback, but we must never lose sight of what is actually feeding back.
Right. But let's look at the mechanics of the system itself. Regardless of the danger of applying it to society, for any system to adapt, whether it's a computer or a missile guidance system, it has to be able to process that feedback.
Yes.
It has to take the error signal
Yeah.
and actually calculate what to do next. It needs a set of rules. It needs to compute.
And to process complex signals, humanity had to invent a way to formalize thought itself into rigorous mechanical steps. And to understand how we did that, we had to rewind the clock just a little bit from 1948 back to 1936 and step into the realm of Alan Turing.
Right. We've figured out how to measure uncertainty, how to send a signal, and how to use feedback. But computation is the engine that drives it all.
Definitely.
Before anyone could build a physical laptop or a smartphone, we had to define what computation actually meant in a pure philosophical, mathematical sense.
If we trace the lineage, it goes back to the 19th century with George Boole, who figured out how to algebraize logic.
Boolean algebra.
Right. He took concepts of true and false and turned them into mathematical operations, which eventually became the ones and zeros of Boolean algebra. But the leap from static logic to dynamic procedure happened in 1936.
With Turing.
With Alonzo Church and his student Alan Turing. They independently published formal mathematical accounts of what an effective procedure or an algorithm actually is.
And Turing did this with a brilliant thought experiment. He imagined a theoretical machine, which he called an A machine for automatic machine, but which we now all know as a Turing machine.
Describe this mental apparatus for us.
Picture an infinitely long tape of paper divided into discrete little squares. This tape serves as the machine's memory.
Okay.
The machine has a head, a physical mechanism that can look at exactly one square on the tape at a time. This head can do a few very simple physical actions. It can read the symbol on the square, let's say a 0 or a 1.
Right.
It can erase that symbol and write a new one. It can move the tape exactly one square to the left or one square to the right, and it has an internal state, like gears shifted into a specific configuration.
It sounds like a wildly primitive typewriter. How does that compute anything complex?
It computes through what Turing called a state formula, or a table of rules. The machine operates on rigid, step-by-step determination.
Give us an example.
Let's say the machine is currently in state A. It looks at the tape and reads a 1. It consults its internal rulebook, which says, if in state A and you read a 1, then change to state B, write a 0, and move the tape one square to the right.
And then it just repeats the process based on the new state and the new square.
Over and over, forever. Turing proved that this dead simple mechanical step-by-step procedure, if given the right table of rules, could compute absolutely any problem that is logically solvable by a finite series of steps.
Wow.
He made mechanical reasoning into a tangible mathematical object.
He essentially proved that you don't need human intuition to solve complex math. You just need enough time, a long enough tape, and the right set of dumb mechanical instructions.
Mm-hmm.
And shortly after this theoretical breakthrough, John von Neumann wrote a document called the first draft of a report on the EDVS. He took Turing's imaginary tape and translated it into the physical architecture of the computers we use today.
How so?
Von Neumann conceptualized a central processing unit to act as the read-write head, a physical memory to act as the tape, and crucially, the idea of a stored program where the rules themselves are stored in the memory alongside the data.
The sources mention chess game as a metaphor for computation, and I think it perfectly crystallizes how abstract this is.
Go for it.
Think about a game of chess. You have a board with pieces on it. The layout of those pieces represents the current state of the system, the data in memory.
Okay.
You have the rules of how each piece is allowed to move. That is the logic, the algorithm. Making a move is an effective procedure. You are following the rules to alter the state of the board, step by step.
And the brilliance of that metaphor is that it highlights how the physical substrate is entirely irrelevant to the computation itself.
What do you mean?
You can play chess with carved wooden pieces on a marble board. You can play it on a glowing pixel screen. You can play it with scraps of paper. Or if you were a grandmaster, you can play it entirely in your head without a physical board at all.
Right.
The computation is the logical, structural manipulation of the symbols according to the rules. It doesn't matter what the symbols are made of.
Which opens up one of the most famous philosophical thought experiments in modern history. The Turing machine and the computers we built from it are entirely syntactic engines.
Meaning they just follow the structure?
They operate purely on syntax. The structure is shaped in the rules of the symbols. If the tape says 1, write 0. But I want you, the listener, to really think about this. Does the machine ever actually understand what it is doing?
Ah, you are poking at the ghost in the machine. This circles right back to Shannon separating information from meaning.
Exactly. When my computer calculates the structural stress of a bridge, or when it figures out the optimal move in a chess game, it is just blindly shuffling ones and zeros according to the state formula.
It has no idea what a bridge is.
None.
Yeah.
It has no semantic understanding of a bridge or gravity or a knight. A pocket calculator doesn't conceptually understand the magnitude of the number 5, right?
No, it simply routes electrical voltage through logic gates in a way that eventually lights up a 5 on the screen. It mimics understanding through perfect structural rule following.
That tension between syntax and semantics has driven decades of debate in artificial intelligence.
It really has. But while philosophers debated meaning, mathematicians realized they had another massive practical problem to solve. We now had mathematical frameworks for transmitting information, regulating systems with feedback, and computing logic.
Right.
But all of this assumed a somewhat passive universe.
Right. If I'm an engineer computing the load on a bridge, nature is passive. Gravity always pulls down. Wind acts predictably. The bridge doesn't actively try to collapse just to spite me.
But what happens when the system you are interacting with isn't a passive bridge? What happens when you are a military general facing an opposing army or a CEO pricing a product against a rival corporation?
The environment fights back.
Exactly. As the saying goes, the bridge doesn't fight back, but an opponent does.
This brings us to a whole new era of our mathematical genealogy. This requires a completely new branch of mathematics that can handle conflict and strategy.
Yes. Up until the mid-20th century, a huge portion of applied mathematics was focused on optimization. Optimization is passive. It's asking, how do we find the absolute maximum or minimum of this function? How do we design the strongest possible airplane wing with the lightest possible aluminum? It is a monumentally difficult calculation, but the error isn't actively trying to defeat the airplane.
The environment is static.
But when you have two intelligent agents interacting, optimization fails because my best possible choice now depends entirely on what I think your best possible choice is going to be.
Oh, man.
And you are making your choice based on what you think I am going to do. We enter the realm of dynamic strategy. We enter game theory.
Game theory. Pioneered by John von Neumann, the same man who designed the computer architecture, and an economist named Oscar Morgenstern, and was later refined beautifully by the mathematician John Nash.
It is the mathematical modeling of strategic, rational choice.
Let's look at how the math actually handles this entanglement. The sources detail how game theory relies on probability mixtures. Imagine a simple conflict. You have strategy A and strategy B. If you always choose strategy A, your opponent will observe this, adapt, and counter it perfectly. You become predictable, and therefore you lose.
Let's use a very concrete example. A penalty kick in football or soccer.
Perfect.
The striker is standing over the ball. He knows he can kick it to the left corner or the right corner. The goalkeeper stands on the line knowing he has to dive left or right before the ball is even struck.
Right.
If the striker analyzes the goalie's weaknesses and decides, well, my mathematically optimal strongest kick is to the left, so I will always kick left, what happens?
The goalkeeper optimizes his own strategy. He realizes the striker always goes left, so the goalie always dives left, and he blocks every single shot. The striker's static optimization leads to total failure in a dynamic game.
So the striker has to introduce uncertainty. He has to mix his strategies. Maybe he decides to kick left 60% of the time and right 40% of the time at random.
Okay, that makes sense.
But the goalkeeper is not a static wall. He is a rational agent running the exact same mathematical calculations. He will adjust his diving probabilities to perfectly counter the striker's 60-40 mix. They are mathematically entangled in a dance of probabilities.
And this dance leads to the defining breakthrough of the field, formulated by John Nash, which we call the Nash equilibrium.
Ah, yes.
A Nash equilibrium is a state in a strategic game where no player can improve their own expected payoff by unilaterally changing their strategy.
It's a standoff.
It is a mathematical deadlock of pure rationality. It means that, given the exact strategy you are currently playing, I am playing the absolute best counter strategy possible. And given what I am doing, you are doing your absolute best.
Yeah.
Even if we completely revealed our secret strategies to each other, neither of us would change our behavior because any deviation would make us worse off.
And this concept exploded. Suddenly, game theory wasn't just about parlor games. It became the mathematical foundation for understanding nuclear deterrence during the Cold War, calculating the grim logic of mutually assured destruction. Wow.
It is used today to design complex economic markets, to structure massive telecommunications, spectrum auctions, and evolutionary biologists even use it to explain why certain animals evolve cooperative behaviors while others are selfish.
But, just as you pushed back on cybernetics being applied to society, we have to look critically at game theory.
Fair enough.
Game theory fundamentally assumes that the players are perfectly rational decision makers who are ruthlessly maximizing their expected utility.
Yes, that is the baseline assumption.
And that is where I have a massive problem. Look at actual human beings in the real world. We are almost never perfectly rational calculating machines. We make decisions based on emotion, on spite, on love, on cultural tradition.
That is very true.
We suffer from extreme cognitive biases. We have bounded rationality, meaning we don't have the time or the brain power to calculate every possible outcome, so we just go with our gut instinct.
Right.
How much of real, messy human behavior does this beautiful crystalline mathematics actually capture? You are hitting on the most fiercely debated topic in modern economics and behavioral science. Game theory provides a perfect mathematical baseline. It illuminates the deep underlying strategic structure of a conflict.
It shows us what pure rationality would do.
Exactly. But if you apply it rigidly to international diplomacy or human relationships without accounting for psychology, history, and bounded rationality, your models will spectacularly fail to predict reality.
Yeah.
Game theory gives us the skeleton of conflict, but human nature provides the flesh and blood, which is much harder to mathematically quantify.
The math models the interaction, but it assumes a perfect interactor.
Well put.
Now, a penalty kick is an interaction between two players. Nuclear deterrence was mostly a game between two superpowers, but look at the modern world. What happens when you take the strategic interactions of game theory and the feedback loops of cybernetics, and you scale them up from two players to millions or billions of interacting agents?
The math fractures again. When you scale a system up to that degree of interconnectivity, you no longer just have a game. You have a massive, complex network.
Right.
And the mathematics must evolve to capture collective behaviors that no single component could ever generate on its own.
This leads us into the realm of networks and complexity. And to trace this genealogy, we actually have to jump way back to the 1700s to a mathematician named Leonhard Euler.
Ah, Euler.
He wasn't looking at fiber optic internet networks. He was looking at a very physical problem in the city of Königsberg in Prussia.
Right. Königsberg was a city built on a river with two large islands connected to each other and to the mainland by 7 distinct physical bridges.
Okay.
The mayor of the city posed a puzzle. Was it possible to design a walking route through the city that would cross every single one of the 7 bridges exactly once without backtracking?
People tried walking it, mapping it, but they couldn't figure it out. Euler looked at the problem and solved it, proving mathematically that it was impossible.
Right.
But the answer isn't what matters here, right? It's how he solved it.
Euler's genius was abstraction. He looked at a map of the city and completely ignored the physical reality. He ignored how long the bridges were. He ignored the size of the islands. He ignored the flow of the river.
You stripped it all away.
He stripped away all the physical geography and reduced the entire city to pure structure. He drew dots to represent the land masses and lines connecting the dots to represent the bridges.
Simple as that.
By doing this, he invented graph theory. He proved that mathematics could study purely structural relationships independent of physical space.
In modern network theory, those dots are called nodes and the lines are called edges. A node is a distinct entity. It could be a person, a computer server, an airport, or a neuron in your brain.
Yes.
An edge is the connection between them, a friendship, a fiber optic cable, a flight route, or a biological synapse.
For a long time, graph theory was a somewhat static, abstract branch of mathematics. But as the 20th century progressed and human infrastructure became vastly more interconnected, telephony grids, power grids, and eventually the internet mathematicians began studying massive dynamic networks.
And they encountered a terrifying and beautiful phenomena.
The emergence.
Emergence. It's the idea that when countless interacting parts connect, they produce collective behaviors that are entirely unexpected and that you cannot predict just by studying the individual parts in isolation.
Give us an example of emergence in everyday life.
The perfect example is a traffic jam on a highway.
Oh, I hate traffic.
We all do.
Yeah.
Let's say you have a single car driving down an empty road. You can study that car's engine, its tires, the driver's psychology, down to the molecular level.
Okay.
But nowhere in the properties of that single car will you find the concept of a traffic jam. It doesn't exist at the individual level.
Right.
But when you put 10,000 cars onto a network of roads, interacting dynamically, a new property emerges. One person taps their brakes slightly, the person behind them brakes a little harder, the person behind them slams on their brakes.
And
Suddenly, you have a shockwave of stop-and-go traffic that travels backward down the highway like a slinky even long after the first car has sped away. The traffic jam is a behavior of the network, not the nodes.
And as mathematicians mapped these massive networks, they began uncovering hidden, universal laws governing their structure. For instance, they discovered the mathematics behind small world networks.
Small world networks.
This is the rigorous proof behind the popular idea of 6 degrees of separation. You might assume that in a sprawling global society of 8 billion people, the path between any two random individuals would be incredibly long.
Yeah, I'd assume so.
But the math shows that because of a few highly connected individuals bridging different social clusters, the average path length between any two nodes is shockingly short.
Right, the person who seems to know everyone in town connects 5 different friend groups that would otherwise never interact.
Precisely. Those highly connected nodes are called hubs, and the study of hubs led to another massive discovery: scale-free networks.
Scale-free, what does that mean?
Mathematicians found that in many real-world, organically grown networks like the architecture of the internet or the network of citations in academic papers, or even the metabolic networks in our cells, the connectivity is not evenly distributed. It is deeply, wildly unequal.
And it follows a mathematical rule of preferential attachment, which basically translates to the rich get richer.
Exactly. When a new node joins a scale-free network, say a new user creating a website, they are mathematically far more likely to link to a node that already has millions of links, like Wikipedia or Google, than they are to link to a random blog with only 2 links.
That makes sense.
This natural dynamic creates massive gravity well hubs. These hubs hold the entire network together efficiently, making communication incredibly fast. But they also introduce massive vulnerability.
How so?
If you take out a few random nodes, the network survives. If a targeted attack takes out a major hub, the entire network fragments and collapses.
So Euler looked at the physical bridges of Königsberg in the 1700s, and modernity used that exact same topological math to map the digital bridges of the World Wide Web.
It's the same math.
In fact, PageRank, the foundational algorithm that built Google into a trillion-dollar empire, was born directly out of this network mathematics. It didn't just look at the text on a web page. It looked at the edges connecting the nodes.
It used the structure of the network to infer invisible semantic value.
Exactly. It turned the hyperlink structure of the web into a mathematical proxy for human trust and importance. If a lot of important hubs linked to a specific page, the algorithm inferred that the page was valuable.
But as the internet exploded, it didn't just remain a static map of hyperlinks. It became a living, breathing entity generating unimaginable tidal waves of noisy data. Billions of users clicking, swiping, buying, and moving.
It's chaos.
Complete chaos. To make sense of it, the static structural math of networks had to marry the dynamic probability math of Boltzmann and Jaynes that we discussed at the very beginning.
We had to shift from mapping fixed structures to creating systems that could dynamically infer, predict, and learn. Fixed, rigid algorithms break down when reality gets messy. A traditional Turing machine program with fixed rules like, if user clicks X, then show Y is useless when you have a billion users with constantly shifting preferences.
Mathematics had to start studying systems that move through different probabilistic states over time. It had to embrace dynamic uncertainty.
The sources mention a critical tool for this called a Markov chain. Now, the way I'm reading the definition, a Markov chain sounds like a system with the memory of a goldfish.
That's a good way to put it.
It's a mathematical system that transitions from one state to another, but its core feature is that it is memoryless. The probability of what happens next depends solely on the current state, and it completely ignores the long history of everything that happened before.
Let's look at how that actually works in practice to predict the future.
Okay, let's build a highly simplified Markov weather model. We define 3 possible states for the world: sunny, cloudy, and rainy. A Markov model doesn't care if it rained every day for the last 2 weeks. It only looks at today.
Right.
The model has a table of transition probabilities. It says, if today is sunny, there is a 70% chance tomorrow will be sunny, a 20% chance it will be cloudy, and a 10% chance it will be rainy.
Okay.
If tomorrow turns out to be cloudy, the model shifts its state and consults a new set of probabilities based only on the fact that it is currently cloudy.
And while that sounds overly simple, when you string thousands of these state transitions together, you can model incredibly complex, seemingly unpredictable phenomena.
Wow.
You can predict the structural future of a system over time, even when every individual step involves inherent uncertainty. It is probabilistic, but highly structured.
And this kind of dynamic probability fueled an absolute revolution in modern data science.
It really did.
Because for decades, traditional statistics was mostly descriptive. You took a sample of data, you found the average, you calculated the standard deviation, and you described the variation. You mapped correlations.
But the new mathematics of data driven by massive networks shifted from describing the past to predicting the future and actively intervening in it.
And the leap from observation to intervention requires understanding causality. This is where the work of computer scientist Judea Pearl becomes monumental.
Pearl is a giant in this field.
For a very long time, statisticians were terrified of the word cause. They chanted, the mantra correlation does not imply causation, and they refused to go further. If rooster crowing is perfectly correlated with the sun rising, traditional statistics struggles to prove mathematically that the rooster isn't causing the dawn.
But Pearl developed the mathematics of causal inference. He explicitly built diagrams and counterfactual math to model cause and effect. He gave us the rigorous tools to ask, if I actively intervene in the system and force variable X to change, what will happen to variable Y?
That is the difference between passive observation and active control. And when you combine Markovian state predictions with causal inference, you get the modern recommendation algorithms that run our digital lives.
Let's look at YouTube or Netflix. When you log in, the algorithm doesn't have a rigid Turing rulebook. It has a massive probabilistic model of human behavior based on millions of nodes in a network.
Yeah.
It uses state transitions to guess what you want to watch next, but crucially, it uses cybernetic feedback.
Norbert Wiener's Cybernetics again.
Exactly. It presents a thumbnail to you. If you click it, that is positive feedback. If you scroll past it, that is an error signal. The algorithm mathematically updates its internal probabilities in real time, learning your specific preferences, adapting its predictions.
The system is learning from its environment. It's no longer just calculating, it is inferring.
And when you step back and look at all the puzzle pieces we've laid out, the statistical entropy of Boltzmann and Jaynes, the information channels of Shannon, the cybernetic feedback loops of Wiener, the rigid computation of Turing and von Neumann, the strategic games of Nash, the massive networks of Euler, and the dynamic learning of Markov and Pearl, you realize we have finally gathered all the raw materials needed to cross a terrifying and wondrous threshold.
We have arrived at the modern day. We're looking at the culmination of this grand genealogy. We are looking at machine learning and artificial intelligence.
We finally take all of this math and build a digital brain.
And remarkably, the theoretical spark that ignited AI didn't happen yesterday. It happened way back in 1943.
It is truly staggering to look back at the timeline. In 1943, a neurophysiologist named Warren McCulloch and a brilliant, eccentric, self-taught logician named Walter Pitts published a paper.
McCulloch and Pitts.
They were looking at the actual wet biology of the human brain, and they asked a seemingly insane question. Could the physical firing of biological brain cells be translated into pure algebraic logic?
When I read the breakdown of this 1943 paper in the sources, it feels like the moment lightning strikes the primordial soup. They look at a single biological neuron.
Right.
They noted that a neuron receives chemical signals from other neurons across its synapses. If the incoming signals build up and cross a specific threshold of excitation within a tiny fraction of a millisecond, the neuron suddenly fires an electrical impulse down its axon.
If it doesn't cross the threshold, it stays completely silent.
It has an all or none character.
Exactly. It's binary. It's a biological switch. It is a 1 or a 0.
And because it is an all or none process, McCulloch and Pitts realized that the messy nervous system could be abstracted and treated using propositional logic.
Yeah.
They mathematically proved that you could build a theoretical network of artificial, simplified neurons that behaves exactly like the logical calculus of a Turing machine.
By wiring these binary biological switches together in specific patterns, they showed you could construct networks that could perform operations like A and D or R and not. They proved that any computable logical expression could, in theory, be embodied in a network of neurons.
They took the cold, rigid logic of Turing's tape and grafted it onto a biologically inspired architecture. But those early artificial neural networks were static. They were just conceptual wiring diagrams.
The massive leap over the ensuing decades, driven by pioneers like Rosenblatt with the perceptron, and later Hinton, Bengio, and LeCun, was figuring out how to make these artificial neural networks learn on their own.
And how do they learn? They learn by combining computation with cybernetic feedback and dynamic probability. Modern machine learning defines an architecture, a model made up of layers of these artificial neurons.
The connections between the neurons have numerical weights, or parameters. In a massive modern AI, there are hundreds of billions of these parameters.
At the very beginning of training, those parameters are completely random. The AI is essentially an infant with zero structural knowledge.
Right. You feed the model an input, say, an image of a cat. Because its parameters are random, it spits out a completely wrong prediction. It says, "That's a toaster." The system then compares its prediction to the correct mathematical answer, and it calculates an error signal.
Cybernetics.
Exactly.
Wow.
The system takes that error signal and uses a mathematical algorithm called backpropagation to send the error backward through the millions of artificial neurons.
Oh, wow.
It slightly adjusts the numerical weight of every single parameter, nudging them in a direction so that the next time it sees that image, it is statistically slightly more likely to say cat.
And you run this feedback loop billions of times on mountains of data, and the system optimizes its parameters until it achieves breathtaking accuracy.
But the architecture didn't stop there. Over the last few years, we saw a massive architectural evolution that gave us the generative AI we see everywhere today.
The transformers.
The sources point to the transformer architecture, and specifically a mechanism called attention. I want to dig into this because this is what powers modern AI.
Right.
Before transformers, AI read text sequentially, left to right, like a human reading a book. It had a hard time remembering the beginning of a long paragraph by the time it got to the end.
The transformer architecture, introduced by researchers like Vaswani in 2017, completely revolutionized how networks process sequence data. Instead of reading word by word, left to right, the attention mechanism allows the neural network to look at every single word in a massive block of text simultaneously.
It mathematically weighs how important each word is to every other word in that specific context, regardless of how far apart they are on the page. It creates a dense mathematical web of context.
And it processes all this language using something called embeddings. And this concept is perhaps the most beautiful piece of systems mathematics we've discussed today.
I agree completely.
An embedding takes a word, like apple, and it doesn't store it as letters. It translates the concept of apple into a massive list of numbers, a vector in a high-dimensional mathematical space.
We really need to build a mental model of this high-dimensional space for the listener because it is crucial to understanding how AI actually thinks.
Okay, let's build a physical space in our minds. Imagine a massive empty room. Let's make the axes of this room represent concepts.
Okay, I'm picturing it.
The vertical axis represents royalty, from low to high. The horizontal axis represents gender, from male to female. The depth axis represents age, from young to old.
Got it.
Now, the AI takes the word king and places it in this room. It has high royalty, male gender, adult age. It sits in a very specific coordinate in the top right back corner.
Okay.
Now, take the word man. It has 0 royalty, male gender, adult age. It sits lower down.
Right.
Here is where the magic happens. If you start at king, subtract the vector for man, and add the vector for woman, you physically move through that mathematical room.
Yeah.
And the coordinate you end up standing on is the exact coordinate for the word queen.
It is breathtaking. The neural network isn't just memorizing definitions. It is mathematically mapping the entire structure of human semantics into a giant multidimensional geometric galaxy.
Words that are used in similar contexts end up physically closer together in that mathematical space.
Exactly. The AI navigates human language by measuring the geometric distance between concepts.
Which brings us to the ultimate inescapable example, ChatGPT and the large language models like it. When I sit at my computer and type a complex philosophical question into ChatGPT, and it types out a flawless, nuanced response in real time, well, it feels like I'm talking to a ghost. It feels like magic.
But when you look at its genealogy, it is simply the ultimate realization of every single concept we have traced today. It is systems mathematics made interactive.
Let's trace the threads. It uses the probability and entropy of Boltzmann to predict the statistically most likely next word.
Yes.
It relies on the massive, scale-free network mathematics of Euler to process billions of connections.
Right.
It uses the cybernetic feedback loops of Wiener to constantly refine its parameters based on human reinforcement.
Yeah.
And it computes all of this on the rigid logical architectures descended directly from Turing and von Neumann.
It is the entirety of our story compressed into a single server farm. But this brings me to a massive final thought experiment for you, the listener. We have traced this entire history. We know exactly how the machine works.
We know that an AI like ChatGPT is fundamentally a massive Markov chain, navigating a geometric space of embeddings, using statistical regularity to guess the next word based on billions of optimized parameters.
Knowing all of that, is it actually thinking? Is human intelligence nothing more than prediction at a massive scale?
That is the defining philosophical question of our era. From a purely functional, pragmatic standpoint, if the output solves complex engineering problems, writes coherent essays, diagnoses medical scans, and perfectly navigates the world, it is operating intelligently.
But it forces us back to the Turing thought experiment. Does it understand the meaning of the words it generates?
Right.
Or is it just the most sophisticated syntactic engine ever created, perfectly mimicking the shadow of semantics through sheer statistical correlation?
It's staggering to consider. Let's synthesize this massive journey. We started with Ludwig Boltzmann staring at the steam and chaos of an engine boiler, trying to mathematically measure human ignorance.
We watched Claude Shannon take that math of uncertainty and map the telegraph line, ruthlessly separating the message from its meaning.
We saw Alan Turing put reasoning onto a mechanical tape, and Norbert Wiener build feedback loops into living and non-living machines.
We saw the math expand to encompass the strategic standoffs of game theory, the massive emergent networks of the internet, and the dynamic probability of data.
And finally, we saw McCulloch and Pitt's neural logic evolve into the artificial intelligence answering our questions today.
It is a breathtaking genealogy, but it does leave us with a critical question about the ultimate limits of this mathematics. What is lost when the entire lived world is translated into data?
Can true human meaning, our culture, our nuance, our irrational bounded rationality, our emotional depths, our capacity for suffering truly be mathematized? Or are we only ever approximating it, creating higher and higher resolution shadows of the human experience? We started this deep dive by asking you to look around at your phone, your thermostat, and the AI on your screen, and to recognize their shared mathematical DNA. So I will leave you with this lingering question to mull over as you go about your day. Look at the AI in your phone right now. Is this the endpoint of this grand mathematical genealogy? Is this true, ultimate intelligence finally realized in silicon? Or is it simply the latest, most complex mathematical mirror we have built to reflect ourselves back to us?
A profound question to leave them with.
Thank you for joining us on this deep dive. Stay curious, keep questioning the invisible systems operating all around you, and we will catch you next time.